I asked Dolly to make an image of a laser beam incident upon a camera. I really wanted a collimated laser beam, but we got this kind of focus beam you see here. But it's not a bad image, but what I wanted was something more abstract, like what we see here on the right. We have an infinite plane wave incident on a lens that's going to focus onto a focal plane. Now, if it happened that the focal plane was one focal length behind the lens, then you know what would happen, that this would come in and focus to a single spot. But that's not what we want to focus on here. We want to say that we're going to image a plane in the beam. So the plane we're going to image is a distance d sub o away from the lens, and it's going to form an image at a distance d sub I with magnification equal to d sub I over m over d sub naught. I said m is equal to minus d sub I over d sub o. Now, who cares about the magnification? The beam is infinite in extent, right? So if I have an infinite extent beam and I demagnify, it should still be infinite extent, right? Well, not really. That's not what happens here. Actually, you get an images that look like this. This is simulations that are available on the course GitHub site. This is for the magnification times the aperture is equal to 128 times lambda f number, and it turns out that the extent of the image that you form is equal to 128 times lambda f number. If we increase the magnification or increase the aperture up to 256 lambda f number, then the extent of the image that we see is 256 lambda f number. Doesn't have anything to do with what's the extent of the object, which is infinite. Only has to do with this product, MA equal to 256 lambda f number, and over here we've made it into 512 lambda f number, and you see that the size of the image increases. So what's going on here? Well, like we said, if we had a plane wave coming into a lens, it's going to focus at a spot here at the focal plane, but then it goes beyond that spot and turns into a more extensive beam. If we just look at the angle here, so this is A, the aperture size, and this is F. So the half angle there would be A over 2F, and the full angle is A over F. And if we multiply that by this distance, which is going to be the image distance, d sub I, which would be the full distance from the lens to the focal plane, or to the image plane, we'll have z sub I minus f would be this distance right here. We multiply the angle times that distance, and we get the extent of the beam. Now, from the thin lens imaging law, we can see that z sub I minus f is going to end up being equal to z sub I over z naught times f. So this d is going to be m times a, like we saw in our previous simulation, what you see right here. Now, there's some ringing, there's some phase terms around there, so we need to figure out what's causing that ringing and what's causing the structure of this image. This is a simulated measurement. This is experimental data from Greg Nero's work in the camera lab at the University of Arizona. We have an object, which in this case is a small circular spot. We image that object through a grating onto an array of cameras, which are back here. It's a 3x3 array of cameras, and you see the images with one image, unfortunately, behind my face, but the other 8 images are present there. And you see that they have this kind of ring pattern and finite size. Now, these are demagnified because the spot here, is a few millimeters across, but the image is only 150 millimeters across, so they're demagnified, and we're seeing this kind of ringing pattern. And then there's this kind of blur that the images for the different cameras that are shifted slightly relative to the optical axis have different kind of phase modulation. We need to figure out what's going on here, and we'll do that in today's episode. Computational Imaging. Episode 37, Phase Curvature. So, episode 36, we talked about the coherent impulse response, the impulse response between the object space, which here we've denoted by x sub r or y sub r, to image space, which for this particular equation is denoted x double prime, y double prime. X sub r is a demagnified measurement, so x sub r is equal to x divided by the magnification where x is positioned in the object space. So we find it convenient to try to make the system shift invariant, which we do by rescaling the coordinates. So now This impulse response is a shift invariant impulse response on the same scale for the x double prime variable in image space and the xr variable in object space. H sub r here is the Fourier transform of the people function, as shown here, evaluated at the spatial frequency x double prime over lambda di. Di, of course, is typically going to be something close to f. But we have these additional phase terms. So coherent systems are measured in complex space and can have phase terms. The shape of the phase terms may vary with lens design. We could put in field flatteners and other components to try to manage the phase, but the system is going to remain sensitive to the overall phase. And as we see here, the actual impulse response is not shift invariant. The phase terms do not depend on the difference between position in the image space and position in the object space. So these terms are going to be kind of interesting for us to deal with. Now, a lot of times people don't really worry too much about the phase terms because we don't measure the field itself. We measure the magnitude squared of the field. So the actual image that we're going to measure is going to be the magnitude squared of the field convolved with the impulse response. So the phase terms in image space will cancel. So this term in e to the I pi x double prime squared, that cancels when we measure the magnitude squared of the field, and the overall phase delay for propagating through the system is not important also because that will cancel out when we measure the magnitude squared of the field. But this quadratic phase term in object space, shown here, does not cancel. We're going to integrate, we're going to multiply the object field by that quadratic phase and then convolve with the impulse response. Now, what's kind of interesting here is that the impulse response, of course, is a low-pass filter. That we've seen that the bandpass of the system is limited by the pupil size. So as we have this quadratic phase term modulating the object, low frequency terms in the object are modulated by this high frequency phase term, and they will not get through the lens. That's what causes this finite size of a plane wave when we image a plane wave with the lens, as we saw earlier, that the low frequencies from the edges of the plane wave do not get through the imaging system because they're modulated by that quadratic phase term. Now, if the object actually has high frequencies, those high frequencies can be modulated to pass through the imaging system. That's an effect that we see here. Again, in simulation, we're imaging a chirped field. So that in the linear space here, we're going from low frequency in the middle to higher and higher frequency as we go to the edge. What we expect to see with an imaging system is that there'll be some blur and the high frequencies are lost. And we've seen that here when the magnification is large, that the fields that get through the aperture are larger, but we see that there's a roll-off in the frequencies, and so the high frequencies don't get through. But here, when the magnification is smaller, we see something interesting, that the actual object has high frequencies here, but we see low frequencies in the image space, and that's because these low frequencies are created by the modulation of the high frequency phase term modulating high frequency terms in the object, which alias into low frequencies in the image space. And so we see here where we should be imaging high frequencies, we see low frequencies because of this physical aliasing effect. We can see a similar thing if the object just happens to have high frequencies. So here, in contrast to imaging a plane wave, we're imaging again in simulation here, we have an image of a certain scene, and the scene has high frequencies in this railing and the kind of lines on the bridge here. And what you see is that here, where we would see nothing if the object field was constant, we see a high-pass filter. We're seeing a high-pass filtered version of the scene coming in from the edges of the field. So we see a larger disk. Here with the plane wave illumination, the disk we saw was 128 lambda f number. We see it much larger now because high frequencies in the object are bleeding through the system. And in contrast, when we illuminated with the plane wave, this is what we saw. We saw something that was exactly 128 lambda f number across, with some ringing due to this kind of phase modulation we have on the field due to this quadratic phase modulation. This is all in simulation. Here's an experimental system measuring the same thing. Now here, we're imaging a field. Now the field here is in microns, so this from here to here is 200 microns. This is an object that's illuminated with a 532 nanometer laser. The focal system is a 25 millimeter lens operating at an aperture of f4 at a range of 500 millimeters. So the magnification is about 1/20, so it's 20x reduction in the image, and so the object size is on the order of 300 microns, which is this magnification times the aperture size. So we have in the case of f4, we have like a 6.25 millimeter aperture. We're demagnifying that by 20, and we get down to about a 200 micron disk here that we're seeing the image. Now, so these two images here and here, these are images of a resolution chart where all we've done is shift the resolution chart, so we're seeing different parts of the resolution chart. The images in the center here, those are overexposed. So these over here, they were exposed at a level where we can see the image in the center of the resolution chart. Here we're increasing the exposure, so this 3-4 here is in this region and way overexposed. But in increasing the exposure, we see that there's field out here that we weren't seeing at the nominal exposure. And the same thing up here, we're seeing a field outside, but we don't see bars, which we should see in the actual chart. What we see is a high-pass filter version of the bars. So experimentally, what we're seeing here is that there's a high-pass filter effect from the edge of the field. And actually, what's happening here is the bandpass for coherent image shifts at different points in the field, shifts linearly. This is kind of a complicated plot, but I'll try to explain it. This is position in object space. This is beyond the optical axis at the center. On the optical axis, the bandpass goes from minus 1/2 lambda f number to 1/2 lambda f number. This is the range of frequencies in the the x component of the Fourier space that we'll observe. But as we move, because of this quadratic modulation, we're shifting the bandpass because we're modulating the field by a phasor, which of course modulating the field by a phasor shifts its range in Fourier frequency space. And what this means is that really that if we have here's our imaging system, for the center of the field where we're coming here, the image that we see here has a bundle of rays that are centered on the optical axis from an image that comes on axis. But if the image comes from up here, the bundle of rays that we're going to see is centered on the ray, the chief ray, the ray that goes through the middle of the lens, and that's at a different spatial frequency than DC. So as we linearly go across an image in a coherent imaging system, the bandpass of the system is, or the position of the bandpass is changing linearly. So as you get, over here, the bandpass is actually at very high frequency for the actual image space. And if the image happens to be a DC image, like a plane wave, then you'll get cut off. That out here, the DC component is just not getting through the lens. Now, we don't see this often when we look at natural images, that if you have a white wall and illuminate it, you'll see a white wall in the image space. That's because it's diffuse. Here's a simulation of a diffuse field. So we've applied a random phase to each point on the object. So this is the same simulation, the same scene as we saw that was being cut off if it was a low frequency DC object. Here, if there's a random phase, a high frequency modulation like diffuse reflection from each point, then there'll be a Fourier component radiated in all directions on reflection, and the object will have its natural size in the object space. Okay, so this phase curvature term is super interesting, and we're going to use that to help us measure phase in imaging systems in just a couple of lectures. I want to look at it a little bit more detail. Now we have again our transformation from the object to the measurement space. So in here we've gotten rid of the XR, so we just make it X. So same equations, but we don't have to keep XR forever. We can just make our impulse response h of x, y. We're going to convolve that with the object field, which we see here. But here we've allowed for the fact that we might shift the object or shift the lens. If we move the camera by this delta x, delta y, we're moving the camera relative to the object space. And as we do that, so we would get a shift in the object by moving it. So this is the same equation as we had before for G, but now we've added these coefficients, delta x, delta y, corresponding to the object's shift. We can change coordinates here to take this out of the object, and that moves it into the impulse response and into the phase term. So this x here would become x minus m delta y when we shift our position in xy space, redefine the x coordinate to make the shift in this coordinate instead of in f of xy. We square that out, and then the term in delta x squared, delta y squared in the exponent goes away because we're taking the magnitude square, so we don't care about an overall phase modulation. And so we just have this kind of linear shift in phase with respect to delta x, or with respect to this delta x, delta y. And now we can think about, like, when delta x delta y was equal to 0, we measured an image, and that image, whatever image we measured of the system, had incorporated into it this quadratic phase mask in object space. So let's just make that a part of our definition of the image that we would measure. So for 0 shift, we would measure the convolution of this f sub p of xy with the 0 shift h. But now as we add a shift, we're going to modulate the image by this phase term. And so this is what happens in an imaging system. If we have an image, we're observing a scene. If we shift the scene by delta x, delta y, that's equivalent in a coherent imaging system to modulating the object field by a linear phase term, linear in the shift. And that's what we're seeing in this image that I showed you in the introduction. We have these different images, different cameras observing the same scene, but their optical axes are shifted relative to the chief ray for the center. So in the center, we're seeing an image that we would see just looking at a disk with this kind of phase modulation due to the quadratic phase modulation. We're not seeing the field illuminating this object is actually a constant plane wave, but we see this kind of circular ring pattern due to the fact that there's a quadratic phase modulation on top of that. But now as we shift that, we see a linear phase shift due to different lateral shifts of the camera. Now, in a couple of lectures, we're going to use this to figure out how to recover the coherent wavefront from a camera by tracking the phase shift as we move a camera. But before we do that, we need to go back to an assumption that we looked at when we derived the impulse response. We looked at two conditions. We looked at the case where we're imaging between, or we're mapping the field between the front focal plane and the back focal plane, and then we looked at the thin lens imaging condition. Of course, those are not at all the only conditions that we could have in the relationship between the input field and the output field. We could have the distance to the input field and the distance to the output field equal to anything we want going through a lens. When we do that, we're going to get defocus, right? The lens will no longer, the image is no longer in a focal imaging condition, but we can still model it. It's a coherent field. We can model what happens. This idea of looking at defocused fields is used in one example of phase retrieval in what's called the transportive intensity equation. We're not going to get into a detailed discussion of transportive intensity equation imaging, but we are going to discuss the impact of defocus. And we will mention the fact that looking at this defocus through the transportive intensity or through iterative algorithms is one method for measuring the wavefront of the field. With coherent images, we've been interested in how to propagate the field, how to measure the coherent wavefront, and then how to image objects once we have the coherent field. In the next few lectures, we're going to really dive into this problem of diverse ways of measuring the wavefront, and we'll start next time by talking about defocus.